So we have seen that how we can write a code for making a small world network in one dimension. What is our next aim is we want to implement the decentralized search or myopic search on this network and look at how does this search perform. So what I'm going to do in this code is we'll look at how do we do a myopic search on this network. So for doing myopic search, we remember what we have to do is we take a node and then we look at all of its neighbors and then we look at the distance of all these neighbors from the target. And do you remember when we look at this distance, we assume that we have no knowledge about the long range context of these neighbors. So we have to look at the distance of these nodes across the cycle. So while looking at the distance, we assume that there is no long link in the network and then we find their distance. So for that purpose, what I'm going to do is the graph G here and then I have added the edges here. So before adding any long link in this network, I take a copy of this graph here. H equals to G dot copy, and why I have taken this copy here is actually very simple. The reason is very clear. What is the reason? When I am going to do myopic search, so in that myopic search I have to find the distance of my neighbors from the target, and while finding the distance I do not have to see the long range ties in the network. So when I have to find the distance, I look in this network H. This network H This network H here is simply my cycle, the cycle which we have formed, which consists of only the ties based on homophily and has no long range link. And then this network G over here, G is the network which consists of the homophily based links as well as the weak ties. So whenever I do my myopic search, I will be performing the myopic search on my network G, but when finding the distance of my neighbors from the target, I will be using this network H over here. Okay. So how do we proceed is, I define a function myopic search over here. Define myopic search, and this needs our graph, the source vertex and the target vertex. So U is my source and V is my target, and we have to find a path from source and target. I take this path as a list, and this path initially consists of only the node U, which is the source. Current is my variable which takes care of where I am standing currently on the network. So currently we are standing on U, and while what we are going to do is, I take a loop over here. What we do is, we have to find the next best neighbor where we have to move on. So I call a function here, find best neighbor. Find best neighbor G current. So I have to find the best neighbor from current, and for finding this best neighbor I will be needing the target. So what I am going to do is, for finding the best neighbor, this current node will be looking at all of its neighbors and will choose the one which is closest to the target in the graph H, not in the graph G. In the graph H where there are no long range ties. So before proceeding further, let me define this function here. Define find best neighbor. Define find best neighbor G, current node and the target. So I take a variable over here, distance equals to G dot number of nodes. You will soon understand why I am taking this variable over here. So what do I do next is, I look at each of the neighbors of this node current here. So for each in G dot neighbor C. So for each in G dot neighbor C, what I am going to do is, I am going to calculate again a distance 1, which is the distance of this neighbor from the target. So for finding the distance of the neighbor from the target, we can use the function nx.shortest path. which gives us the shortest path between two nodes in a graph, and next dot shortest path in the graph H. So you understand why we are taking H here, because we have to look at the distance across the cycle, not across the complete graph. We have to ignore the long range ties. So H, and what is my source? So here this is the source for my shortest path. So the shortest path function requires three parameters: the graph, the source, that is the first node, and the target, which is the second node, across whom I am finding the distance. Please do not confuse it with the source and target over for our myopic search. The source and target for myopic search are different, and these source and target are different. So when we were doing the myopic search, we were at a node current, and now this node current is interested in finding the best neighbor, and for all of its neighbors it is calculating their distance from the target. So here this source here is nothing but the neighbor of my node current. So the source is what? Source here is each, which is the neighbor, and target here is V. So the target is actually the same, the source changes. Now what I am going to do is, if this distance is less than the previous value of distance, which was quite high, so we want this value to be quite high, and if my distance 1, it is less than distance, what I am going to do is, distance equals to distance 1. So this is a simple method in coding which we use to find out the maximum value or the minimum value, and I set the value of choice, the best neighbor, to be equal to each, and at the end I return choice. So I think that this is pretty clear, and then I return back to my code for myopic search. Here I have find out the best neighbor for my node current, and after finding this best neighbor, I append this best neighbor to my list, to my path, and then the value of current becomes equals to this neighbor which I have found. And also while doing this, if the value of current becomes equals to V, which is the target, then what we have to do is simply come out of this while loop, and then we can return the, so we can return path actually. So we return path here. Okay, so this is the code for our myopic search, and we return path here. Okay, how do we execute it? So let's say P equals to the path which I wanted to find out, and myopic search, and let's say I have performed the myopic search, let's say from the node 0 to node 40, and I wanted to see how this path looks like. I'm going to play around with colors a little bit here. What I'm going to do is, I'm going to call a function here, set myopic path colors. So I know, so I guess you know what I'm going to do here. So when we are going from this node from 0 to 40, I want to see how does this path look like. So what I'm going to do is, I'm going to define a function here, function for set myopic path colors, and here I have to pass my graph G and the path P, and it gives me an array called colors. And let's define this function here. Define set myopic path colors, and what this function is going to do is, for I have a array here C which is for colors for each in G dot nodes. What I am going to do is, if each equals to, let's say P0, which is the starting node of our path, what I am going to do is, for each in G dot nodes, if each is the starting node of our path, I am going to append let's say red color here, and if each equals to the last element of my path, then also I am going to append red. So what I am going to do is, the source and the target here are going to be red. The source and target here are going to be red, and are going to be red. We call it's not actually else if, it's elif, and else if each in P. Okay, so if it is the starting node of this path P, we append a red here. If it is the end path of this list P, of this path P, we append a red here. If it is neither starting nor end but exists in P, so what I am going to append there is, let's say, blue. And what do I do? For rest of the nodes, I make them yellow. So all the nodes in my graph are now going to be displayed in yellow. The starting and the ending nodes are going to be red, and the rest of the paths on my nodes on my path are going to be blue. And then I return. See here, you'll soon understand why I am using colors here. And then we got colors here, and next row draw G node underscore color equals to colors. And let's now see, execute it and see. Okay, line 52 shows an error. So I've commented this portion over here, and let's now execute it and see. So you can see that when we have to find a path from this node 0 here to 40, so we can go from 0 to 2, 2 to 38, and 38 to 40. So this is the path which my myopic search gives you, and the network here looks quite random. So we know why it looks random over here, because we have added a lot of long range links to this network. So what I am going to do is, I am going to change this value of T here to, let us say, 10. So let's add only 10 long range links over here, and we know that the initial diameter of this network was nothing but 25. From that 25 diameter, after that I have added 10 long range links, and then I find my path from the node 0 to 40 using my myopic search. And let's see. Okay, now you see the path length has increased quite a lot, and this is my ring network, although it doesn't appear here quite like a ring. So I start here from node 0, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes in between. So within the path length here is 12. So the myopic search here finds a path of length 12. What next I am going to do is, we have seen that the myopic search is not an optimal search. Let's now compare the myopic search to my optimal search, and what we are going to do now is, we will find the optimal distance, let's say, from this node 0 to 40 only. So what I am going to do is, I am going to find another path, and this path is nothing but the shortest path, the optimal shortest path on my graph G from node 0 to 40. So you see here I am applying the shortest path on the graph G. So this graph G here is consisting of the long range links also, and then I find P1. And what actually we can do here is, I want to see a different path also. So here what I am going to do is set optimal path color. So I am also going to set optimal path colors here based on the path obtained from here, from G to P1, and then this is going to be quite easy. So we are going to use the same code which is here, and let's say, so here it is G P1, and then P1, 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 and what I am going to do is, the starting node is red, the target node is also red. The middle nodes on this optimal path, let's color them green, and the remaining nodes in the network are yellow, and then we return C. And let's now execute this code and see the difference between both the paths. Okay, source, I'm very sorry, source equals to 0 and this is target equals to 40. Now let's execute it and see. Okay, set optimal path colors. So this is set optimal path colors. Okay, so you see this network over here. Okay, so there is an error. So what is the error? When I am doing this set optimal path colors, I have recolored the nodes which I have found in the myopic path. So we have to be a little bit careful. So what we will do is, here when we have to find colors, we will actually have to combine both these functions. So let's say set path colors G, P and P1. Okay, G, P and P1, and then we need only one function here. Set path colors G, P, P1, and what I am going to do is, obviously what is, if each is P1 0, it is P0 also, because the source node is same red, and then here it is red, and if each in P1, then we are making it green. And you see here, one node can be both in P and P1, right? So if there is a node which is present in both P as well as P1, and it is neither the source node nor the target node, we are coloring that. Okay, please be careful with the colors here. We are coloring that node to be yellow. Okay, so yellow is a node which occurs in both these paths P and P1. Else if each in P is the path for myopic search, what we are going to append here is, for myopic search we are going to use blue, and else if each in P1 it is, then we are going to append green over here, and else it is in none, we are going to append a black over here. So please see, all the nodes in this network are going to be black. The source node is red, the target node is red. The nodes which are in the path for myopic search are blue. Nodes which are in path for optimal search are in green. And the nodes which are in the path for both the myopic search and the optimal search are in yellow. So we are going to make it a little bit more rigorous and more understandable. What we are going to do is, okay, if each in P and P1 and each is not equals to P1 0 and each is not equals to P1 length of P1 minus 1, which clearly says that if each in P and P1, it's in both the paths, but it is neither equal to the source vertex, not equal to the target vertex, then we are going to append a yellow here. If each in P and each node in P1, then we are going to make it blue, and if each in P1 and let's say each node in P, then we are going to make it green. So instead of an else if here, we can use the if here, here also we can use the if, and at last, if each node in P1 and each node in P, we are going to make it black. Now let's execute it and see. So here you see there is no node common between both of the paths. If you look at the myopic search, it starts from 0 and goes to 40. It takes this path 0 to 2 to 4. Okay, it is actually little bit difficult to make out where this path is going. So before 30 there is 28. Okay, so this path goes something like this. The ending path is clear. Okay, let's see, from 0 it goes to 2. 2 is somewhere here. From 2 it goes to 4, which is here, and then to 6, 8. So it goes all the way here, and then it comes here, here and here, and reaches 40. And while an optimal path starts from 0 and goes like this. So we can see that optimal path is much shorter than what our myopic search is finding out, which clearly shows that our myopic search is not the optimal search.